Well, good morning. It's been a busy few days, so I'm going to take a bit of a break now and get back to the 432A. Where we left it was that the broken unit here, the course adjust pot is in fact working. So there appears to be some problem somewhere else. Now, I already know, you can see the cable attached here. I already know that this is a good cable and sensor because I've tested that. And I know that this set of stuff over here, the A1 and A2 boards, and then the chassis underneath it are good because I've tested those. The piece that we don't know is these three here, the chassis, the A1 and the A2 board. So what I thought I would do is just swap some components around and see if we can identify the problem. So the first thing that I'm going to do is take the good boards and slot them into the chassis from the non-working unit and see if it will course zero. So let's go do that. So here we have the two good boards, and we have the non-working chassis. So let's turn the unit on. Okay. And let's try turning that. Oh, there we go. So we're on course zero. So we can see that with the good boards, we do get course zero working correctly. So it's either going to be the A1 or the A2 board. Now, we know that the A1 board works because in a previous video I swapped the A1 board into the working unit, and that's where we sort of identified, or I went down the wrong path looking at that potentiometer, the course zero potentiometer. So let's turn it off and swap in the A2 board from the non-working unit. Okay, so I have the A2 board in now. So now let's see if the unit will zero. So we're getting that non-zero again, and if I change here, you can see that changing the course zero value doesn't actually change the needle at all. Now, the needle here, as you can see, is in the recharge battery section. And how the battery works, I don't have a battery in it, and I don't have the battery charging parts. But theoretically, there is a voltage put in to the A2 board that causes the meter to drive down here to say, hey, you have to recharge the battery once the battery drops below the minimum voltage. So we might be looking at something like that, or we might be looking at somewhere else. Now, as is typical of devices of this era, HP provided some great troubleshooting information. Now, the manual is a little on the early side, so it doesn't go through troubleshooting really detailed step by step and explain and check and so on. What it does is provide some troubleshooting trees, but more importantly, it provides some information around the what you should see in terms of the voltages and the waveforms. So let's go ahead and have a look at that information that is on the A2 board and see what happens. So this is printed out from the manual, and we can see that we have some test conditions and then some voltages that we should get on the test points. Now, I'm going to ignore all the A1 because that board seems to be working correctly. So we'll hold that for the moment. And then test points 3, 4, and 5 test the rails. And we've already had a look at those. And as nominal values, they're close. The minus 13 is a little low. Drink of choice today is a Diet Coke from my SodaStream. I like having the SodaStream at home because it lets me control the amount of syrup that goes in. I find a lot of the canned and gun, trigger drinks at bars and restaurants and that to be overly sweet. Anyway, what we have in the manual is a set of waveforms. So if we take a look at the set of waveforms, you can see them on this page here. And what you'll notice is consistently they're showing, these are the old school actual photographs, I think, of the screen display with a little cover over it so that the camera can attach and so on. But point 2 here, test point 2 is going to be our 5 kilohertz multi-vibrator that drives the rest of the circuit. And then these test points will allow us to walk through. So let's take a quick review of where those test points are. So here we go. This line here shows where all of the A1 board is, with the exception of the A1 Auto 0 unit, which is treated as its own potted component, if you remember that big grey square that was on the board. Test point 2 that we were seeing here comes directly from the 5 kilohertz multi-vibrator. And then we can start looking at the signals at each stage so that we can work our way through the blocks to see where the problem is. This current switch up here is where that signal for the battery comes in this block that will drive this up. So you can see that the feedback circuit follows through here. So if we're getting good signal here, here, and here, then we can look down this path to see if we're getting a good signal to here, and then we might want to look at the low pass filter to see if there is something there. And if there's nothing there, then there might be a physical problem with the board getting back to here. Now, this feedback path will go down to those cinch connectors that the boards plug into. And we know that the physical chassis is good because we just tried swapping in good known boards. So this return here, physical return, is on the board. So maybe there's an issue on the board, and there might be some more components in the path that might affect that. So let's set up and go and have some readings and check those waveforms. Okay, so we're all set up. Now, I'm using my Rigol, it's off screen here. I refuse to run ultrascope. It's just a steaming pile of fetid dingo's kidneys. So what I'm going to do is I'm going to capture the wave as we see it, and then put that on the screen as an image while we'll talk about it in post-processing. All right, so let's turn the unit on now. And the first thing I'm going to do is check item 2, test point 2, which is the 5K multi-vibrator. Okay, so let me go and look at our frequency. And if we have a look at the frequency down the bottom, you'll see that it's around 5 kilohertz, so that's good. There is some bouncing around at the bottom of that signal. So if I capture a couple of single things, you'll be able to see that there is a difference in the height of that. Now, an image of that, you'll see that the image does look like what we were expecting here. As you can see, we're expecting it to be roughly 10 volts and to be around 5 kilohertz. And that's what we're seeing here. We're seeing 10 volts per division and a frequency of around 5 kilohertz. So let's move on to the next point. And if we have a look here, we've just measured here. So now 6 and 10 are our two outputs that should be showing signals that are similar to what we're getting in that item. So let's go to test point 6. Here we have the scope set to what the image shows for 6. And so now you can see as I rotate the course 0, we're seeing the change. So now we are in fact seeing a pattern very similar to that. So let's go, where was the next point? Let me grab my little board. So we want to do 10 next and see what's going on there. So 10 should give us that output. Okay. So if you look here at the test point 10 signal, you can see that it's got a slight slope up. That's to be expected. And again, if we look at what we're actually getting on the scope here is a bouncing around. It's not a very consistent, but these are single paths. So if I take a single shot, you can see that we are in fact getting that same similar sort of output that we would expect on that image. So what is that telling us? Well, again, if we come back here, what we're seeing is that our voltage to time converter, which is this guy here, we should be getting 5 kilohertz, which is roughly what we're getting, signal, and it's going to have the pulse width proportional to the compensation plus the RF. And we had a look, if we have a look at 6, what we saw was comp minus RF with the amplitude proportional to that, which is why when we moved the course, the course 0, we saw that change. So now let's go back, let's go through 7, 9, and 8 and see what we're getting. Yep, and if we have a look at the image, you'll see that we're getting what we expect to see there. And remember that changing that course 0 will affect everything. So let's have a look at 8. Okay, well, if we take a screenshot of that, you'll see what I'm getting there on 8. And let's take a single. So that clearly does not look like what we're expecting. This is not quite the correct schematic because this is a later revision of the board. There is a switch added to the board that was added to decrease the settling time during calibration, because you would basically measure stuff, turn these parts, wait for the meter to settle down, and then do it again. And so they added a switch that you could flick to calibrate that would basically take a capacitor out of circuit. So if we take a look here, you can see that 8 goes into the electronic switch that was in that block diagram, that then basically goes through the meter. There is a filter circuit here. It heads out to the recorder, and then it heads back to pin 7 and 8, I think, or pin 8, there we go. And that then follows back in. That's the pin on the cinch connector. So we're not getting the right signal there. 9 isn't correct either. So if we follow the incoming signal, basically what is coming in is through here. Let me make sure I'm on it. It's coming in through here, goes down, goes through the range switch, comes up here, goes through the calibration amplifier, then goes into that electronic switch, and then appears at the meter. And the other path comes up through here and then goes in there. So 10 we saw looked sort of okay. So that path up here is okay-ish. And then this path through here seems to be where the problem. Now, we measured the test point here and test point here. So I think what we'll do is we'll go back and have a look here at this block and think about where we might start looking through here to make sure that everything is working, and travel our way down through that path. So that's sort of where we are for the next episode. I hope you found this step of the process interesting, and I'll catch you again later. Bye.